In Lesson 4.2, Area, we will begin our study into the second major domain of calculus, that is, finding the area underneath a given curve. Now, just like when we learned about derivatives, we're going to start very, very difficult. Remember with derivatives, we started with that big, ugly definition and then found ways to make shortcuts out of things. We're going to do very much the same thing with area under a curve. This particular lesson is going to involve adding all kinds, really millions, really an infinite number of little bitty rectangles that all start at the axis and rise up to the function. And there's going to be an infinite number of these. We're just going to add them all up somehow, and that will give us the area under the curve. Now, in subsequent lessons, we'll learn a way to simplify this process quite a bit, but we better learn the conceptual underpinnings now. So what we're going to do is we'll talk about these different summation formulas. Remember, summation is signified by the capital Greek letter sigma. And essentially what we're doing is adding together a whole bunch of things. And these things, in this case, are going to be these rectangles. So we'll have to find out how wide each rectangle is. We'll have to find out how tall each rectangle is. And then somehow we're going to add them all up. And it will be beautiful. So, before we begin any of our examples here, really what we should do is look at some of these summation formulas. We'll talk about where one of them came from and how they're used. And from there, we'll be able to evaluate some actual summations. It'll be fun, it'll be exciting, and it starts now. Before we get to any of these summation formulas, I think it might first be important to explain what all the pieces of the summation mean. So all of our summation formulas are going to be in the form, this capital Greek letter sigma, which signifies sum, sigma for sum. There's going to be an index of summation, and usually we use the letter I, although it could be really anything. That index of summation is going to be what changes in each term. So what we're going to do is we're going to have a bunch of summation terms that I'm going to call A sub I. They could be something very simple, like simply I itself. It could be something very, very complicated, but it will involve somehow or another that index of summation. That will be what gets repeatedly added. So, again, our index of summation will be I. We will begin at some value that we will call the lower bound of summation. So in our very first term, I will equal whatever value is here. And it will go up by 1 each time until we get to the upper value of summation, which is this n. So all this will do is write out a whole bunch of terms. The first one, the I, will equal this lower bound right here. And in the very last term, I will equal that upper bound. And that's how summation works. So let's take a look at a quick example. Let's say we wanted to do the summation from I equals 1 up to 10 of just some value, let's say 2. Now, this particular term right here does not involve I in any case. So when I equals 1, this will be 2. When I equals 2, this will be 2. When I equals 3, well, again, this will be 2. And for I equals 4, and so on and so on. So the question is, how many of these terms will there be? Well, if we start at 1 and go up to 10, that tells us that we will have 10 terms that are all literally just 2. So what's going to happen when we add all those up? Of course, what we'll have is that 2 10 times. And that will lead us to our first of the 4 summation formulas. If we're summing just a constant, then we're going to multiply that constant by the number of terms we're writing it out. And our sum will simply be C times N. All right, so that was fairly obvious. I could show you that by example here. Let's take a look at this next one where each term is actually just that I by itself. A famous story about Carl Friedrich Gauss, one of the most prolific mathematicians of all time. Well, in the late 1700s, when he was in elementary school, his teacher gave him the task of adding up the first 100 numbers. That is 1 plus 2 plus 3 plus 4, and so on, all the way up to 100. Now, you and I might sit there and actually try adding them all up. But Gauss, he was a genius. He found some patterns in it, and in under a minute, he went back up to his teacher and said, the answer is 5,050. Now, of course, the teacher was quite impressed. I wish I was a fly on the wall to see how that episode went. But Gauss was correct. The first 100 digits do sum to 5,050. Perhaps because of his genius, we now have this second summation formula. After all, when I equals 1, this is simply 1. When I equals 2, this is 2. And when I equals 3, and so on and so on. That will continue up until we have I equals n, which in this episode that I just told you was 100. And again, we said that added up to 5,050, and I'm going to show you how. It's using, Gauss did it his own way, and if you search on the internet, you'll find how he did it. It's actually quite ingenious. He added the 1 and the 100 together to get 101. He added the 2 and the 99 together to get 101. The 3 and the 98 went together to give 101 again. So we notice all these repetitions of 101. Perhaps because of that, we have this formula. Sigma from I equals 1 to n of I. In other words, the first n digits is actually going to add up to n multiplied by the first value greater than n, all divided by 2. Try that for n equals 100 and see what you get. Are you as genius as Carl Friedrich Gauss? Well, you're using the formula, and he was around 8 years old, but, whatever. So, no more stories. Let me just go ahead and tell you these other two summation formulas. If we're summing I squared, that would be like 1 plus 4 plus 9 plus 16, all the way up to n squared, whatever n is. If we add all those up, what we're going to get is this pretty nasty looking thing, but it's a lot better than actually adding them up, so we'll go with it. N multiplied by n plus 1 multiplied by 2n plus 1, and that will all be over 6. So there we go. If we're adding the squares, we get this nasty thing, but again, it's better than actually adding. And finally, if we're adding together the first n cubic numbers, the way that's going to end up is simply n squared multiplied by n plus 1 quantity squared, all divided by 4. So what is the point of all this? Well, in our next two examples, we're going to look at some pure summation formulas that we want to add up and find out what they equal. But beyond that, this is going to help us when we're dealing with linear, quadratic, cubic functions. This is going to help us to deal with those rectangles that I was talking about earlier. But before we get there, let's go ahead and take a look at example A and see how easy this actually is to do. In our first example of using these summation formulas that we just learned, here in example A, we're going to sum all the values from I equals 1 up to 10 of I squared plus I minus 1. Now, what exactly do these numbers look like? Before we start working it out and finding out what the sum is, let's actually take a look at these. If I equals 1, we're going to have 1 squared plus 1 minus 1, which of course is just 1. What happens when I equals 2? Well, that's going to be 2 squared plus 2 minus 1, which if I did this correctly should give me 5. How about when I equals 3? That would be 3 squared plus 3 minus 1. That's 11. And so I see that I do have some kind of progression going on here. I have 19, I'll follow that with 29, and I can just keep going and going and going. Of course, there's only 10 terms, and in fact, the very last term is 109. So if you want to, go ahead, write them out, add them up yourself, try to do it without a calculator, and see how it all works out for you. It's not that fun. So perhaps what would be better would be just to use these summation formulas. Now, the summation formula for I squared, if you recall, I squared is n times n plus 1 times 2n plus 1 all over 6. Of course, I'll stick the number 10 in for n and see how that works. I, as we discussed, that's Carl Friedrich Gauss's formula. That's n times n plus 1 over 2. And finally, for the minus 1, that's just going to be minus, well, c times n. And c, of course, is given as 1, so it'll be 1 times n. So there we go. All I got to do is stick in my n for all of these. And in this case, n, as I said, is 10. So how is this going to look? Well, we'll have 10 times 11 times 21 all over 6. That'll take care of my first term, which in fact is 385. Then we'll add that to 10 times 11 over 2, and that is actually going to work out to 55. And then finally we have this 1 times n, and that is, of course, just going to be 10. So if we go ahead, put those together, what we're going to get is that this sum is going to be 430. Now, did you go ahead and add up those actual numbers? If so, and if you did it right, you should have gotten the same result we did. But which way was quicker? Writing out all these numbers and hoping you don't make an error, and then, I know you grabbed your calculator and started tapping in the key. Or you can just use the formulas. Stick in the value for n, work it all out. 430. Easy as cake. Let's try one more example before we move on to some practical reasons to actually use this stuff. Example B, good times. So here in example B, we have much the same situation going on. We're doing the summation of this thing that we see here. And just for fun, if I want to write out the first few terms just to see how this thing looks, I can start at 2, I'll move on to 10, I'll jump up to 30, way up to 68, and I can keep writing these out. There's only going to be 10 of them total, but I do need to be very careful not to make any errors. Certainly my last number should be 1010, and then I can go ahead, add those up, and see what I get. However, I'm going to do it a little differently. I'm going to pretend like there's more than 10 terms. If there were 100 terms, I would never want to write them all out. And so what I could do is turn this summation thing here into the sum of I equals 1 to 10, and I'm going to rewrite this as I cubed plus I. That'll be a little bit easier for me to deal with because I know both of those formulas. So if I do this, well, I cubed, if I stick 10 in there, is going to give me 10 squared multiplied by 10 plus 1 squared, and that will be divided by 4. And then I'll need to add I. And of course, we've already talked about I. I is going to be the 10 multiplied by 10 plus 1, and that's going to be all over 2. And maybe this 10 should have been in blue, but it all works out in the end. So if I go ahead and simplify this a bit, of course, this is 100 times 121 divided by 4. This over here is going to be 10 times 11 divided by 2. And this is really not too difficult to do. This one will give me 3,025. Over here, I'll simply get 55, add those together, and I'll get what I would have gotten if I had chosen to write out all 10 numbers and then add them up. That would be 3,080. So which way is easier, writing out all the numbers or using the formulas? Well, writing out the numbers might be easier if the upper bound of summation is low, like 10. But what if we went from I equals 1 to 100, or I equals 1 to 1,000? Or, I hate to say this, what if we go from I equals 1 to n and do the limit of that as n approaches infinity? We're going to end up writing out an infinite number of terms. That could get ridiculous. And so hopefully there's a shortcut to this that we'll find shortly. I hope. Anyway, before we talk about any shortcuts, let's go ahead and take a look at the area under a very simple curve. We'll learn about lower and upper sums by building rectangles that start at the x-axis and rise up to the function itself. Well, I'm talking, but let's go ahead and actually take a look. And so for examples C and D, we're going to find the area under this curve y equals x squared, a very simple curve to deal with. And we're going to find the area under that curve by simply building rectangles, as I said. Really easy, no big deal. And it says what we're going to do is we're going to use 4 rectangles that each have a width of 1/2. So we're going to start here at 0, and we're going to conclude here at 2 by simply building these rectangles. I'll have a rectangle between here and here that has a width of 1/2, a rectangle between 1/2 and 1, between 1 and 1.5, and then between 1.5 and 2. So you can see I'm going to have 1, 2, 3, 4 rectangles. So how is this going to look? Well, for my first rectangle, because I'm doing a lower sum, I'm going to raise my rectangle up to the point where it first hits this graph. And so our first rectangle actually is not going to be too exciting because it hits the graph immediately. Why is that? That's because f of 0 is 0. So I have this rectangle here. It has a height of 0 and a width of 1/2. So let me go ahead and write this here. The area, well, our first rectangle, like we said, has a width of 1/2 and a height of 0. So there's our first rectangle. Now our second rectangle, let me go ahead and draw it here. And there it is. So it looks like it actually has a height of 0.25. Where did I get 0.25? Well, I noticed that f of 1/2 is 0.5 squared, or 1/4. So this rectangle is going to have a width of 1/2 and a height of 0.25, which I could call 1/4, but whatever. All right, so time to build our third rectangle. Let's go ahead and rise it up there. And you can see that our third rectangle is going to raise to a height of 1. 1 is where it first hits our graph. And so this rectangle has a width of 1/2 and a height of 1. See, this is pretty easy. Now let me build up our fourth rectangle, and there it is. And where exactly is this? It looks like 2.25 where it hits the graph, but just to make sure, let me run it through my function. So I'd have 1.5 squared, which, yes, is in fact 2.25. That's going to tell me the height of that rectangle. So it has a width of 1/2 and a height of 2.25. Now, if I go ahead and add all these up, of course, what am I going to have? 0 for the first one. The second rectangle has an area of 0.125. The third rectangle has an area of 0.5. And the fourth and final rectangle looks like it has an area of 1.125. So if I add all of those rectangles up, what I'm going to find is that my lower sum approximation of the area under the curve y equals x squared from 0 up to 2, the lower sum approximation is 1.75. Now, you might be asking yourself, okay, that's a lower sum approximation. Clearly, the area under the curve is more than 1.75. So perhaps what we should do is, instead of rising up to when we first hit the function, maybe we should rise up to where we next hit the function. That will give us what we call an upper sum, and that's what we're going to take a look at now. Clearly in example C, we underestimated the area under the curve. In example D, we're going to purposefully overestimate the area under this curve. And the reason we're going to do that is because the true area will fall somewhere in between example C and example D. I'll show you what I'm talking about. We're going to do this the same way we did the lower sums. We're going to build up some rectangles. So if I go ahead and set this up, my area is going to be, here's our first rectangle. It, just like before, has a width of 1/2. But this time you'll notice that it rises up to a height of 0.25. All right, so I'll go ahead and put that in as the height of our first rectangle. Our second rectangle will have a width of 1/2, and how high will it go? Well, there it is. There it is. Notice that our second rectangle actually has a height of 1. This is very interesting. These are the same numbers we saw before, although shifted a little bit. Well, let's take a look at our third rectangle. There should be no surprise that our third rectangle has a height of, there it is, 2.25. All right, so the width of 1/2, height of 2.25. And finally, our last rectangle, let me show it to you now. There it is. Of course, this one has a width of 1/2. And how tall is this rectangle? Of course, it goes all the way to the top. This one has a height of 4. And so, again, it's just rectangles. The entire question is, do I want to go up just underneath the graph, or do I want to go just up right above the graph? Either way, I am hitting the graph. But let's see. If we add all these up now, this first one will be 0.125. This next one will be 0.5. The third rectangle will be 1.125. And the last rectangle, as you see, has an area of 2. So again, if I add these up, I'm going to get an overestimate of the area under the curve, and that overestimate is 3.75. So this is very interesting. We did an underestimate and got 1.75, an overestimate of 3.75, and the true area under the curve is going to fall somewhere in that interval. Now, don't jump to conclusions. Don't think you can just average these two together and have the true area. This is not a linear function. If the function were linear, perhaps you could average the lower and upper sums. But in a case like this, where the graph is parabolic, averaging it really is not going to work. So that's going to bring us to our next example, in which we're actually going to use the definition of the area under a curve. It pays homage to the lower sums and to the upper sums. But this is a way of saying, how can we get a more accurate answer? Clearly, we can kind of squeeze the rectangles together, make narrower rectangles, and of course there'll be a lot more of them, so that would be a pain in the rear to work with, but it would work. And how can we make it even more accurate than that? Well, instead of using really narrow rectangles, how about use even narrower rectangles? In fact, if we can make these rectangles have a width of almost 0, what we could do is have an almost infinite number of rectangles and add all those up. That would give us an extremely accurate area. So that's actually what the definition of area involves. We're going to narrow down these rectangles until they're almost non-existent. And we're going to find the height of each one of those almost infinite number of rectangles and then add them up. Of course, we're not going to add them by hand. We're going to make use of those summation formulas that we learned earlier. But again, I'm just rambling on. So let's go ahead and take a look at the definition of area under a curve. Now, before we talk about this definition of the area under a curve, we do need to check one condition, and it is very important that this condition be met, or else this definition will not work for us at all. See, in order for this to work, the function that we're looking at must be continuous and positive over the entire interval that we're finding the area of. In other words, from x equals a up to x equals b, this function must be continuous and non-negative. Now, if it's not continuous, there's not a whole lot we can do to fix that. But if there are any non-positive portions of the function in that interval, it's only a matter of just adding a constant, and that will raise the function up so the whole thing is positive. Of course, that brings up a whole issue of other things, but we'll deal with that later. For now, let's just assume that we are dealing with a function that meets this one condition. If that's the case, again, we're going to divide that interval into a whole bunch of little rectangles. And this delta x right here will represent the width of each one of those rectangles. This f of c sub I, this on the other hand, will represent the height of each rectangle. So let's go ahead and start by looking at the width. If we have an interval from A to B, and we only want one rectangle, how wide will that rectangle be? Clearly, it'll be whatever B minus A equals. That will be the width. But that's not a very accurate rectangle to use. So let's use two rectangles. What would be the width of each of those? Well, it would be the length of the interval, B minus A, divided by 2. Again, not very accurate, but it's getting at the point. If we want 10 rectangles, we simply take that interval, the length of that interval, and divide that by 10, and so on and so on. So the width of each rectangle is simply going to be the length of the interval, b minus a, divided by n for however many rectangles we want. So b minus a over n is the width of each rectangle, and how tall is each rectangle? Well, that we need to worry about what the actual function is. See, for the width, only the interval matters. For the height, only the function itself matters. So c sub I is simply going to represent each rectangle. It's going to start at the left endpoint of our interval, and we're going to add I multiplied by the delta x. What does this actually mean? Well, whatever a is, that's the beginning of our interval. That kind of makes sense. I is going to be the ith rectangle. For the first rectangle, I is just 1. For the 10th rectangle, I is 10. And so on and so on. and we're going to multiply that, whatever rectangle number we're talking about, times the width of each rectangle. So in other words, this width plus this width plus this width plus this width, and that gets us to the ith rectangle that we're talking about. It's a little bit confusing, but just think of it as a series of rectangles. Each rectangle has a width of b minus a over n, and the height of each rectangle is simply f of whichever rectangle and line we're looking at. So let's actually go ahead and take a look at an example, see how this all fits together, and you'll see that it's not really quite so confusing once you start getting into the math of the whole thing. So let's go ahead and take a look. For example E, we're going to revisit the same graph we were looking at in examples C and D. That's y equals x squared, as you see here. Now, in examples C and D, we built rectangles up, and we're going to do something pretty much the same for example E, except this time, these rectangles are going to be way, way, way too narrow to actually draw on here. If we did draw each individual rectangle, we'd have one like that. There'd be another one like that. There'd be one like this. And there'd be an infinite number of rectangles in between those rectangles even. So we don't want to go through and mathematically find the width and height of each one and add them up. It would take way too long and would be quite painful, to be honest. So our definition of area is that area is the limit as n approaches infinity. That's how many rectangles we want. We want as many rectangles as possible. So we'll limit n to infinity. And we'll follow that with the sigma from I equals 1, that represents the first rectangle, up to the nth rectangle. And again, remember, n is going towards infinity. So there's going to be a lot of rectangles here to deal with. Now, the next step of the process is we're going to do f of c sub I. So we're going to have to take a minute and figure out what c sub I is. But that'll be the height of each rectangle, and then delta x will be the width of each rectangle. So before we get into this too far, let's talk about what is delta x in this case. Remember what we said. Delta x is simply the width of each rectangle. And in this case, that's going to be b minus a divided by n. And remember, we're limiting n to infinity. So the width of each rectangle is going to be, well, as close to 0 as we can possibly get. Now, our c sub I, if you recall, that is a plus I delta x, and that's a mess. But a is where we start, and we're actually starting at 0. And then we have I times delta x. Delta x, which is b minus a over n, well, b minus a we know is 2. So the width of each rectangle is actually 2 over n, and we're going to use that here. So what are we going to find out? We're going to say that delta x equals 2 over n, and we're going to say that c sub I is actually 2 over n I. So there we go. There's everything we need, and now we can take these and put them into the summation formula. What we'll have is the limit as n approaches infinity, sigma from I equals 1 to n, f of c sub I. Well, remember that f of x is x squared. So what is f of c sub I? That's simply going to be c sub I squared. So I'll write 2 over ni, but we're going to square that. And then delta x, as we've already discussed, is simply 2 over n. Now, let's go ahead and expand that a little bit. Basically, what we're going to have is the limit as n approaches infinity of the sigma of, well, let's work this out. This is actually going to be 8i squared all over n cubed. So that's really what this comes out to be. Let's go ahead and break this down some. The n is essentially a constant as far as the summation goes, because the summation only depends on I. So what we'll have is the limit as n approaches infinity. We'll bring the 8 over n cubed out. That's not important for the summation, but the limit will deal with that. So we'll have the summation as I equals 1 to n, and inside the summation thing, what we'll simply have is just I squared. Now from here, it's just a matter of plugging in your summation formula and multiplying that out and using it. And I'm going to leave that as an exercise to you. But what we should end up with, if you do it correctly, is the limit as n approaches infinity of and this is going to be after I distribute the 8 over n cubed throughout, what we should end up with is 8 over 3 plus 4 over n, and finally plus 4 over 3n squared. Again, do the math, verify that this is in fact correct. And what you'll see now is as n approaches infinity, this first term stays at 8/3. The second term, 4 over n, as n approaches infinity, simply just goes to 0. And 4 over 3n squared as n approaches infinity also goes to 0. And so what that means is that the area under y equals x squared from 0 up to 2 is actually equal to 8/3. Now, it's a little bit of work, and you have to think quite a bit to get this to work out for you. You got to figure out what is delta x, and based on that, what is c sub I, and based on that, what is f of c sub I. But if you plug everything in and do your math correctly, it will work out for you. In fact, just to make sure that this works out, let's do one more example before we conclude this lesson, and this will be example D, part 2. So here in our last example, we're going to find the area under the graph of this function right here, which is 4 minus x squared. And what we're going to do is we're going to try to find that area between the bounds x equals 1 and x equals 2. So essentially what we're trying to find is this area that I've highlighted in blue. Now, how are we going to do this? Just like before, we're going to divide this area into millions and millions and millions of rectangles, and they shouldn't be slanted like I drew them there, but millions and millions and an infinite number of these rectangles. So before we do that, what's going to be the width of each rectangle? Well, of course, remember, that's just the length of the interval divided by n. Well, the length of the interval here, if we're just going from 1 to 2, that's just going to be 2 minus 1 over n, or put more simply, just 1 over n. Now, c sub I is going to be just a little bit different here. Remember that we've always said that c sub I is a plus I delta x. And in our previous example, a was 0 because we started our area at 0. But this time, it's a little bit different. This time, we're trying to find the area between 1 and 2. And so a, our lower bound, is actually going to be 1. And then we'll add I delta x, which is actually just going to say 1 over n I. So there we go. We have our delta x. We have our c sub I. And now all we need to do is run these through the definition of area formula. Again, that's the limit as n approaches infinity, because that's how many rectangles we want. We'll do sigma from I equals 1 to n. That'll represent each rectangle along the series. F of c sub I. Well, f of c sub I is actually going to say 4 minus c sub I squared. So 4 minus, here's our c sub I, and I need to square that. So there is f of c sub I, and then we need to follow that with delta x, which in this case is just 1 over n. And I apologize for all of my writing flying together here, but there we go. So I can simplify this a little bit. I still need to have my limit as n approaches infinity. I won't be able to get rid of that until the end. But this 1 over n factor does not depend on I at all, so I can move it out front. And then what I'm left with is the sigma from I equals 1 to n, and I can simplify this whole thing down and make it look like it says 3 minus 2I over n. And then the last term will be minus I squared over n squared. Now, if you're wondering where did this come from, I simply squared this binomial right here and then did 4 minus the result of that. And this is what I got. Now, the next step is simply to use the summation formula on each one of these terms. And if I do that, I'm actually going to skip a step here and leave that as an exercise to you. But if I do the summation formula for each of these, 3 is a constant. So that will turn into 3 times n. Then I have this minus 2I over n. Well, you know what I is. I is n times n plus 1 all over 2. And so what that means is this term is actually going to end up looking something like 2n n plus 1 all over 2n. And you can see where I get that if you actually take the time to substitute the summation formula in for the I. Now, for this last term, this I squared over n squared, I'm going to do pretty much the same thing. The way this is going to look, it's going to say n times the factor n plus 1 times the factor 2n plus 1. And I will divide that. Of course, the summation formula says divided by 6. And we do have an n squared on bottom, so that'll be all over 6n squared. This does not look like a lot of fun to do. But if you go ahead, multiply it all out, distribute this 2n over the n plus 1, and multiply all this stuff right here, what we should end up with is the limit as n approaches infinity. And, well, do all that and then distribute through this 1 over n. 1 over n times 3n is simply 3. When I take care of this this middle part here, what I'll get is 1 plus 1 over n. You'll see that for yourself if you actually distribute this and then multiply it by 1 over n. And then this last term is actually going to say 1/3 plus 1 over 2n plus 1 over 6n squared. Do it for yourself. You'll see where that comes from. It's not too bad. Now, our last step in this whole thing is we'll go ahead and limit n to infinity every time that n shows up. And if we do that, well, 3 remains at 3. The second term will be 1 plus 1 over n. Well, 1 over n is going to go to 0. So really, we just have a 1 here. And then for our last mess right here, 1/3, that's still here. But 1 over 2n goes to 0, and 1 over 6n squared goes to 0. And so this is all we're left with. If we do 3 minus 1 minus 1/3, we'll get our actual area, which for this region is 5/3. And so that's how this whole thing works. We had to find delta x, we had to find c sub I, run it through our equation, do a lot of math, which quite honestly, I didn't show you all the math, but you should be able to do that yourself. And we get down to a result at the end. So here in lesson 4.2, we've actually covered quite a number of things. Remember that this entire lesson is all about finding the area under a curve. So we began by looking at a bunch of summation formulas, so that if we have a constant or a linear or a quadratic or even a cubic function in terms of I, we can deal with that by substituting these formulas in for the I squared, I cubed, or even the constant. So we did a bunch of summation formulas and did a couple examples dealing with that. After that, we took a look at what we called upper and lower sums. What that involved was actually constructing rectangles that either were purposefully underestimates or purposefully overestimates of the actual area. Now, we could only do that with a set number of rectangles. If we wanted to do this with 100 rectangles, it would be a big pain in the rear. So we kept it to 4 rectangles, did that, added up all the areas by hand, and it wasn't too bad. We'll revisit this idea later in the chapter using a shape that's much more accurate than rectangles. I'll give you a hint. It's trapezoids, but we'll get to that later. So it was just a matter of building and calculating areas of rectangles. After that, we took a look at the definition of the area, and that did involve a limit because, as we said, 4 rectangles was not enough, 10 rectangles was not enough. We would never get enough rectangles to be completely right unless we do the limit as the number of rectangles approaches infinity. That definition of area forced us to look at the width and height of each rectangle, and so we said, well, the width of each rectangle is simply the length of the interval divided by n, and the height of each rectangle was based on the function whose area we were calculating. So remember that we simply wanted an infinite number of infinitesimally narrow rectangles, and once we added those up using our summation formulas, we found a very, very, very accurate representation of the area. So it involves a lot of stuff, but if you keep these notes by you while you're working on your assignment, I promise things will be a lot easier. And with that, I will wish you good luck.